Today is going to be pretty basic. We're just going to go over some material that I cover in the 100 level astronomy class here at WVU. If this is really basic, just let me know and we'll go faster. But we deal a lot with scientific notation and units. Astronomy is the study of things that are really, really big by and large, and so our normal units that we use here on Earth are a little bit funky, and so we use scientific notation to express the large numbers more compactly. And then units, we have our own units, again, basically for the same purpose, to take big numbers and turn them into something that's more manageable. Then we're going to go into where we are in the universe. How did we get to our current location? And then importantly, how are we moving? So I only have about one slide on how we're moving, but as we'll learn next week, that's actually probably the most important thing in this lecture is figuring out how the Earth is moving in the universe. There's many different motions, and those actually will show up in your spectrum. All right, lots of words on this slide. So we usually teach the SI system. Astronomers have a second, stranger system called CGS that we sometimes learn, but we're not going to deal with that. We'll just use the SI system for length, mass, time, and temperature. Length is the meter, mass is the kilogram, time the seconds, temperature is Kelvin. We also have light years, which we use to express distance, as I'll show you on the following slide. We have parsecs, which is another unit of distance. Astronomical units, we will not use these very much, but this is the distance from the Earth to the Sun, the mean distance from the Earth to the Sun. Oftentimes we will use solar masses or solar luminosities. We have to peg something to a known quantity. Usually that's easier than using the full SI quantity itself. All right. Students often get confused by this. You guys probably wouldn't, but a light year is a distance, although it has the word year in the name. It is a distance. It is the distance that light travels in 1 year. It's about 9 by 10 to the 15th meters. Again, this is kind of a cumbersome number to use, whereas the number 1 for 1 light year is much more convenient. So just remember, light years are distances if that ever comes up. Here's a little quiz for everyone. The Earth is 1.6 by 10 to the minus 5 light years, or 8.5 light minutes from the Sun. The Sun exploded. How long would it take us to find out? It is about 8.5 minutes. So it's fun to think about that too. This comes up not in this class, but when we talk about cosmology, that the universe that we see today is very different from the universe in this exact instant because of the light travel time. So we can actually see back into the past by looking at more and more distant objects. Within our solar system, we're talking about minutes up to hours. It's not a big effect. But in the whole universe, we can see back to very soon after the Big Bang. All right, scientific notation, you all know this. We'll just leave it up here for a second and then we'll move on. We just have to count the zeros, of course. So count up all these zeros and you'll get 4 by 10 to the 13th. If it is less than 1, you count the zeros, including the 0 to the left of the decimal point, and you get a negative exponent. So this one is 1 by 10 to the minus 10 meters. You all know this stuff, and we won't use these very much here. This is just a slide One thing I will be using is mega for 10 to the 6th and giga for 10 to the 9th, or billion for 10 to the 9th. So it's good to have those handy. Kilo, of course, you're probably more familiar with, like kilometer. We'll be using those a lot. As far as the numbers less than 1, we won't really use these very much, so we can almost ignore this slide. We're going to only be dealing with big things. Sometimes I have my students in the 100 level do this. I'm going to skip it in the interest of time today. The one that actually is kind of useful, actually let's not completely skip it. What's this? This is 10 to the, what's the exponent for 100 billion? 12. Close.
A billion is 10 to the 9th, right?
A billion is 10 to the 9th.
Oh, 10 to the 11.
It's 11, yeah. This is kind of a cool number. It's approximately the number of stars in the Milky Way, or some people think it's about 4 by 10 to the 11th. It's in the range of 1 to 4 by 10 to the 11th stars in the Milky Way. That's a huge, huge number. It's larger than anything you encounter in your daily life, and it's really hard to wrap your brain around how big that is.